So, okay, shall we start? Okay. We start. Yeah. The final speaker in the morning session is Professor Debanjana Kundu from University Texas Rio Grande Valley. She will talk about recent progress on Mazur's growth.
Thank you for the introduction, and I would like to thank the organizers for giving me this opportunity to speak. So today I'm going to talk about some recent work that I've been doing with Antonio Lay and with Ryland Gajek-Leonard and Jeffrey Hadley towards conjecture of Mazur on growth numbers. So we have been seeing Iwasawa theory for the last week and a half or so, but I'll still just to set notations, write down some very basic facts. So I'll start with, and for those of you at the back, if my handwriting gets a little small at some point, just tell me to write a little bigger. So Q sits inside Q1, so on, Qn, Q cyclotomic. So each Qn is sitting inside Q adjoint zeta p to the n plus 1, where for me today, p will always be bigger than or equal to 5. But of course, this stuff that I'm writing down is true for all primes p. So Qn is the nth layer of my cyclotomic ZP extension that is sitting inside the p to the n plus 1 root subunity adjoint to Q. And if I have K will be my imaginary quadratic field over Q. So this is Z mod 2. There will be a cyclotomic ZP extension that I can always construct. And there is another interesting ZP extension that I can construct over K, which is Galois over Q, that is called the anticyclotomic ZP extension. This is non-abelian over Q. On the other hand, K cyclotomic is abelian over Q. And I will often write something like K cyc n to sort of say this is the nth layer of the cyclotomic ZP extension of K. Now, we can look at the compositum of K anticyclotomic and K cyclotomic. That is a ZP2 extension. And I will write that as K infinity, but with a curly K. This is a ZP2 extension of K, and there are infinitely many ZP extensions that are contained inside of this script K infinity. So what is the main question of interest for today? If I have an elliptic curve E over Q that I've sort of base changed to K, I can ask how does the rank of the elliptic curve grow as I go up the layers of a ZP extension. That was sort of started by Mazur in the 1970s, asking that sort of a question. And the question of interest today is, how does the rank or the Mordell rank of E over K grow in the ZP extensions of K? So not just the cyclotomic or the anticyclotomic extension, but in all the other ZP extensions as well, which are sort of supported by K. So in the cyclotomic and in the anticyclotomic extension, this sort of a question has been studied for a very, very long time. So maybe I should tell you a little bit about the history of this problem. So in the 1980s, this goes back to combining the works of Kato and Roerlich. We know that if you look at the Mordell-Weil rank, okay, whatever, the Z rank of the elliptic curve over the infinite ZP extension of Q, that is finite, and this is not just true for Q. In fact, this is true for any abelian extension over K. 80s, okay, maybe 90s. So what does this really mean? It means that if I'm going up the layers of the cyclotomic ZP extension, the rank will stop growing at some layer. That's great. And if you're seeing this maybe for the first time, I just want to point out that this is not the Mordell-Weil theorem, because this is an infinite extension. Mordell-Weil theorem is for a number field. So just pointing that out. Okay. So we know about the cyclotomic ZP extension. So now you can ask about other ZP extensions. And in this regard, we have a conjecture that we call the growth number conjecture. This is due to Mazur. As far as I know, this was first written down in the ICM proceedings from the ICM in Poland. But if there is an earlier reference, please let me know after the talk. But as far as I know, this was first formulated in that ICM proceedings. And what does he predict? He says, let E over Q be an elliptic curve, and P be a prime of good ordinary reduction. Then, okay, I'm going to then the Mordell-Weil rank of E stays bounded in any ZP extension of K except the anticyclotomic one, unless, so this is, so if I write K infinity without the curly K, that means just a ZP extension of K. So this is unless K infinity is K anticyclotomic, and the root number of E over K is -1. I want to make a few quick comments about this conjecture, especially for the experts in the audience. So the way Mazur actually formulates this conjecture is not for the Mordell-Weil rank. He actually conjectures it for the ZP corank of the Selmer groups. But if you're willing to assume finiteness of Shah, then of course these are equivalent statements. And for a motivation purpose, I like to sort of say this is a conjecture about the growth of Mordell-Weil ranks. Any theorems that I will be stating later on will be for the Selmer groups. And the other thing is, Mazur's conjecture is a lot more precise than the way I have stated it over here. He states it in terms of what he defines as a sign. And that sign is not always the sign of the functional equation. In the generic case, which is the case that we will sort of stick with today, it is the sign of the functional equation, and this simplification is okay. But if you're in what Mazur calls the exceptional case, then you need to be just a little bit more careful. And that was sort of touched upon in Professor Kobayashi's talk yesterday. Yes.
E should defined over Q, or this can be applied for a curve defined over K?
Okay, that's a good question. Maybe he phrases the conjecture for any elliptic curve defined over K. But whenever I'll talk about it over Q. So maybe in his conjecture, he does not require the elliptic curve to be defined over K. And another comment is he did phrase the conjecture for P ordinary, but there have been extensions of this conjecture to the supersingular case. Of course, in that case, you're no longer talking about the ZP co-rank of the Selmer groups, but you're talking about plus minus Selmer groups. But there are extensions of this conjecture to the supersingular setting. But if you, again, sort of think about it from the Mordell Way rank kind of a formulation, then the formulation remains the same. So what is known, and this is, I'm going to go over this very quickly because, again, Professor Kobayashi did sort of explain this result yesterday, but it feels like maybe I should at least mention it in my talk. So that's going to be the exceptional case of Mazur. And this is, the elliptic curve is defined over Q, and it has Cm by OK, where K is an imaginary quadratic field. And in this setting, due to the work of a lot of people, including Greenberg, Gros-Zagier, Rohrlich, and Rubin, we know Mazur's growth number conjecture in completely. So what does that mean? It means, so, okay, again, if P is ordinary, then we know that the rank of the elliptic curve in the K infinity ZP extension has the following growth shape. So it's bounded independent of n as long as K infinity is not the anticyclotomic extension, or if the L function has even order 0 at x equals 1, order 0 at s equals 1, and in the complementary case, so K infinity is the anticyclotomic and the L function has odd order 0 at s equals 1, the growth shape is 2 p to the n plus some constant c. And in this setting, you actually also have precise growth formula for the supersingular setting. So you know that if you're going up the anticyclotomic tower, the rank is unbounded. You can make that more precise. You know which layer it's growing and by how much. If you're in any other ZP extension, then the rank growth is bounded. So this was what was known in the 90s, and as per my knowledge, there was not a lot of work being done towards this conjecture for a very long time. And what is new is what I'm going to talk about now. So for this, I should. So there is some recent work of Sujata with her collaborators. So Klein, Matar, Sujata. There is recent work of mine with Rylan Gajek Leonard, Jeffrey Hatley, myself, and Antonio Lay. And then there is my work with Antonio Lay. So I will sort of tell you what the status is and what these three works sort of do in general. And then I will sort of just focus primarily on the third column. So it's kind of always very scary to sort of talk about results of people who are in the audience, but this is what I understand from their paper. This is the sort of setting in which they can answer Mazur's, they can prove Mazur's growth number conjecture. So if the rank of the elliptic curve over K is 0 and P is ordinary, then they show that Mazur's growth number conjecture is true. And in the root number 1 case, they have a result which says if the lambda invariant, so this is the usual Iwasawa lambda invariant attached to the Selmer group of the elliptic curve over K cyclotomic is at most 1, then, and P is again ordinary, then Mazur's growth number conjecture holds. And I think they're also able to sort of tweak this a little bit. They can vary over some other families and show that if the lambda invariant is less than or equal to 1 over some other ZP extensions, then also they're able to make such a conclusion. I don't want to say too much about their work, but something that I understand is their proof is fairly algebraic, and they actually find a very interesting connection between Mazur's growth number conjecture and another conjecture in Iwasawa theory, which is called the MHG conjecture. And it's using sort of their progress towards this other conjecture that they're able to attack this question. But this is what they did. And my work with Rylan, Jeff, and Antonio, this was, again, a fairly algebraic result. And we were able to sort of address similar cases, but just a little different. So there are different examples from what you would encounter in their theorem. So the first thing is we also can attack the rank 0 case, but for the rank 0 case, we're actually also able to sort of talk about the P supersingular. So rank Z, EK is 0, P ordinary or supersingular. That's something that we are able to do. The rank 0 case is sort of naive. It's not too bad. And instead of using their lambda invariant condition, we have a slightly different condition, which is closely related, but a little weaker, but it will come at a cost. So, okay, so the replacement for lambda would be that we will, okay, I have not introduced what is y, but that's fine. We will, so if y is the cyclotomic variable, then I'm going to look at the multiplicity of y in the characteristic ideal of the Selmer dual and ask that to be less than or equal to 1. And this is just like a little weaker than their lambda invariant condition. No, over here we're p-ordinary. So it is just for the rank 0 that we have the super singular. And we don't get into, because we're asking for rank 0 even over k, we're not really falling into the whole super singular. This one is ordinary. This is p-ordinary only. It was just over here that we could sort of talk about the super singular case. Here, again, we're just back to p-ordinary. And this weakening of the lambda condition will come at a cost, and that's what we call a semi-cyclicity hypothesis. And that just means that over the ZP2 extension, we actually want our Selmer group, dual of the Selmer group, to be a direct sum of cyclic torsion modules. So direct sum of in other words, we're asking for that pseudo-isomorphism to be like an isomorphism on the nose. Of course, this is a very algebraic condition, but we are able to provide arithmetic situations where these hypotheses are satisfied. So just to sort of say it in words, if you assume like nice things like Heegner hypothesis holds, P does not divide the Tamagawa number, P is what we call a non-anomalous prime, and you ask for the P part of SHA for K to be trivial, not just finite, but you ask for it to be trivial, you can make these conditions hold. So the main thing that I want to focus on today is my work with Antonio, which is not an algebraic result. This is going to use some analytic tools. And again, we will only stick to the p-ordinary situation. I don't think so. So if you look at the arithmetic conditions, yes, but as an algebraic result, we still have a slightly weaker hypothesis. That is possible, yes. I will have to go back and look at the examples that we have in our paper, but that is very much possible. But okay, so in the analytic situation, so we will ask for P to be split in K. We will ask for the generalized Heegner hypothesis. I'll tell you in a second what that is. We will ask for 1/2 of the Iwasawa main conjecture, which, again, I'll make some comments about that. We will ask for the P portion to be trivial over K. And we will have a condition on a p-adic height. So in particular, if I write Z Hague to sort of denote the Heegner point over K, then I want that. I'll tell you what this p-adic height is, but I would need a condition on this that the p-adic height is non-trivial. And what we're really going to talk about over here is, I mean, the way we are going to sort of approach the Mazur's growth number conjecture in this case is that we will use the cyclotomic derivative for the two-variable p-adic L function and relate this to a certain cyclotomic height of Heegner points over the anticyclotomic tower, and then we are going to be able to attain the theorem that we want. So the, okay, maybe I'll just tell you what GHH is in a second. This is just asking for, if you look at the conductor of E, the number of primes that are, okay, you can write it as n plus n minus, where plus is the number of split primes in K, and n minus is the part which is inert in K. I'm asking for this to be even. The number of primes which are inert in K is even. Okay. Before I start going into the proof, I would probably want to make a few quick comments about some future possibilities. So this proof actually generalizes in a fairly easy way to cases of GL to abelian varieties. And that, at least in some cases, this is something that I've already done with Antonio, but I still wanted to talk about the elliptic curves case because it's sort of easier to talk about than the more general abelian varieties situation. One major flaw of at least both these methods in the is that it's almost impossible to generalize these to higher rank situations. We have like no way how to attack what would happen if the elliptic curve had rank 2 or higher over K. And none of these methods sort of seem to generalize to the supersingular setting. Like, yes, the rank 0 you can sort of say because that's very naive, but in these other cases, there is no way of attacking the supersingular situation. So those are sort of pitfalls. But anyway, I'll tell you about how we go about proving this theorem. So to set some notation, I will write script G to mean Galois K infinity over K, which is isomorphic to ZP2. And okay, so nope, it's not right. So the Iwasawa algebra, I think I want to write it as lambda infinity, and this is two variables, x and y. Y will be my cyclotomic variable, and x will be my anticyclotomic variable. So this is going to be the kernel of G to gamma cyclotomic, which is Galois K cyclotomic over K. And ouch. And tau will be the kernel for G gamma anticyclotomic. I think I have that right. Maybe I should say sigma maps to 1 plus x and tau maps to 1 plus y. So if I want to talk about the other ZP extensions that sort of lie between the cyclotomic and the anticyclotomic ones, I will introduce the following notation. Okay, so if K infinity over K is any ZP extension, you can find a unique pair AB in A colon B in P1 ZP such that sigma to the A, tau to the B corresponds to that ZP extension. And what ZP extension is it? It's kernel of some ZP extension gamma infinity, and this one is what I'm going to denote by gamma A comma B. That's my notation. So this is Galva KAB, KAB over K. And I will have another notation, which is H, which is the Galva group of strip K infinity over KA comma B. So that's like the top guy. So KAB is a ZP extension over K, and then you have something up to K infinity. So H is that top guy. I should probably denote this by H, A comma B as well. So what is the Iwasawa algebra lambda AB? This is going to be something in one variable. Of course, this is again just notation. So in this notation, I do want to sort of say that gamma cyclotomic is going to be gamma 1, 0, and gamma anticyclotomic is going to be gamma 0, 1. And again, cyclotomic was my y variable, anticyclotomic was my x variable. And maybe a couple more small notation that will show up when I start writing. So talk about FAB to be 1 plus x to the A, 1 plus y to the B, minus 1. And I'll have a projection map, which is going to be the map that goes from lambda infinity to lambda AB, which you can, I think, identify over as I'm going to leave this notation up on the board so that I don't have to repeat what these are. So in this setting, we do have a p-adic L function that is due to Herenru. So it's a two variable p-adic L function. Again, for simplicity, I'm just going to assume p is bigger than or equal to 5 throughout. So this p-adic L function that I will write as LP x comma y, this lives in QP tensor lambda infinity. Okay? And I can take its projection to the anticyclotomic line, which is LP x comma 0. So I've just taken the projection to the anticyclotomic line. And this is going to show up right now. So what I can do is I can write this p-adic L function in a new way. What I'm going to do is I'm just going to expand this as a power series in my variable y with coefficients in QP tensor lambda anticyclotomic. So what am I doing? I'm just going to write this as LP x comma 0. This is like going back to first year calculus of sorts, just two variables. Y, x comma 0, y plus d2LP, y squared, x comma 0, y squared, and so on. Now, this, so we have this. Yes, I do, thank you. So what happens is in the sort of setting that I'm in, so I've assumed the generalized Heegner hypothesis. So what, is it okay for me to write here? Maybe it is. So what the general Heegner hypothesis is going to do is it's going to allow me to say that the sign of the functional equation over K, of E over K is -1 at S, yes? And then it's a result of Castella that in this setting, you have that this term is actually 0. So under GHH, we have this term is 0, so we only have these remaining terms, which are all multiples of 1. Okay. So that is going to be kind of crucial for us. I just don't want to, at least for this purpose right now, I don't want to have to worry about which result is proven for p equals 3 if I need more hypothesis. So I just want to assume p bigger than or equal to 5 to like keep it simple. Yes, they do. I don't think we wrote it up for p equal to 3 in this paper, but in my more recent work, we do sort of work out the p equals to 3 cases now. Right, okay. So, right, now what is the cyclotomic lambda cyclotomic lambda anticyclotomic height pairing? Attic height pairing. So you have a height pairing that goes from the compact Selmer group, P, so T is the Tate module, over P anticyclotomic. Again, that's the Tate module over the anticyclotomic. And you can make sure that its image sort of lies in QP tensored lambda anticyclotomic. And this anticyclotomic height pairing, you can sort of not just look at what's happening at the top, you can sort of look at what is happening at each layer. So at each layer, you have a height pairing that you can sort of denote by n. I'm just introducing this notation because I'll need this in a second. And then there is work of Daniel Debanjana from 2017, and then there's subsequent work in, I think, 2020. And his result is extremely general, and I'm not going to write it out in full generality. But basically, what one can obtain from his work, if you sort of restrict to our very specific setting, is the following. If you look at the p-adic L function, you look at its cyclotomic derivative and evaluate it at 0, 0. So I'm plugging in x equals 0, y equals 0. Then this is actually equal to some non-zero multiples that I don't want to write down what this is, of the pairing of the Hegner point, but you're looking at it at the base level. So this is what you can sort of obtain from Daniel's work. And now I will sort of introduce the Iwasawa main conjecture. I only need 1/2 of it. So what I need is that, yes. So the point is, this is how it's defined, but I just want to sort of make sure I mean, I'm not writing down exactly how I'm obtaining from. Yes. I didn't understand your question. Could you repeat that again? Sorry. Yes. Yes, and then when I'm sort of like looking at what happens at the base, this is what it's going to correspond to. This is like, as I said, this is like I'm writing it as a very, I don't know, but I'm not going to comment on that, at least not on record. I don't know what I'm going to get if I, for example, take a partial derivative with respect to x. At least the way we derive it, it does. Whether one can get it independently, I don't know. Okay, so this periodic L function is going to live in the characteristic is going to live in cell E over K infinity dual. That's one half of the Iwasawa main conjecture. But I probably should make a comment here that there is work of Ashay, Francesc, and Chris Skinner, which sort of proves this half of the Iwasawa main conjecture, at least under some minor hypothesis. And from what I understood from Marco's talks last week, probably even that hypothesis is no longer required. So if you want, you can actually no longer think of this as a conjecture. This is a theorem. We'll have this inclusion. So, okay, look at LAB. This is LP x comma y mod my FAB over there. So this is basically equal to, under appropriate identifications, the restriction of the periodic L function, and this is now going to lie in here. I'm calling that I. So the first key result that we prove, and this is basically the main step. I'm going to provide a proof after completing the basic argument. So if AB is in P1ZP, but not the anticyclotomic, it's not the anticyclotomic ZP extension. If you assume that this periodic height pairing is not zero, then you can show that the periodic L function, which is which you're projecting under the AB on the AB line, that's going to give you something that is non-zero. And the second result is something much more standard. So this is where we will use Daniel's work and also require the hypothesis that I had written down initially, that I want the pairing to be non-trivial at the base. So the second result, which is more standard, is I can show in this case that the dual Selmer group has over ZP2 has no non-trivial pseudo-null submodules. And once you have both of these, the way you obtain the main result is the following. You look at, so because it has no non-trivial pseudo-null submodules, you will get a short exact sequence coming from the structure theorem, which basically looks like this. This is going to be, the quotient is going to be something pseudo-null. Now you can take homology and get, with respect to HAB, where AB is whatever your choice. So, okay. So I'm avoiding writing everything. Then you will have direct sum. I think you have pi AB at II. And then you'll have the H0, H, B, and this goes to 0. The pseudo-nullity hypothesis will guarantee that these two objects are lambda AB torsion. Then using result 1 and the Iwasawa main conjecture, again, you can show that this is lambda AB torsion. So that means your dual Selmer is lambda AB torsion. And then a standard control theorem argument guarantees that the Selmer over AB is torsion. And once you have that as torsion, it's again fairly standard argument going back to Greenberg, who will tell you that the growth shape will therefore have to be in any ZP extension, which is not the anticyclotomic one. You will have a growth shape which is as predicted by Mazur. So that is going to be something which is, so it's going to be, sorry, it's going to be bounded because it's torsion. So shape is as predicted. By Mazur. And now you will ask me, well, what about the anticyclotomic? So that actually goes back to the work of Ben Howard from, I want to say 2004. And he had actually shown in that paper that if you are in the anticyclotomic tower and you satisfy the sort of hypotheses that I've been talking about, you get Mazur's growth number conjecture. So the anticyclotomic was taken care of by Howard. The cyclotomic was taken care of by essentially by Kato and Verlick, and everything in between, we sort of prove it using, under our appropriate hypotheses, using this analytic technique. So how do we go about proving? Sorry. Oh, result 1. Does this depend on? Oh, wait, this is a hypothesis that I need. This, okay, this hypothesis of this being non-zero does, no, this, okay, this hypothesis does not depend on AB. If that was the question, then yes, this does not depend on AB. Like, yes, that hypothesis does not. How much? Okay, I have 5 minutes. I can probably very quickly give a sketch of the first result. So I think I made the blunder that I was afraid I would. So we had LP XY. I should not have erased it. This was DLP dy x0 y. That's half d2LP dy squared x0 y squared, so on and so forth. So I'm assuming it's my extension is not the anticyclotomic one, so A is not equal to 0. I can do appropriate manipulations and make sure that either A or B is a p-adic unit. And I'm just going to sort of show you the argument for when B is a p-adic unit. The other argument is fairly similar. So, okay, so I'm working now in the Iwasawa algebra lambda AB. I can rewrite Y. So remember I had FAB, which was written in terms of X and Y. So if I move variables around, I can write it as 1 plus X to the minus A over B minus 1 mod FAB. So I can do this. I can now replace this into this equation and also use the fact that 1 plus X minus AB raised to the power minus AB minus 1 has a sort of very nice shape when you look at it modulo X squared. So modulo X squared, this object becomes something like 1 minus A over B X. Now, when I plug all of this back into my first equation here, what I'm going to get is, okay. Right. And yeah, so I'm also taking the projection, the appropriate projection, because I'm going to do mod FAB. So this becomes minus A over B over dot CB, and this is going to be modulo some X squared. Oh yeah. Right. And now if I take the derivative with respect to this variable XAB of my left-hand side and evaluate everything at x equal to 0, what one would notice is you get minus A over B d dy 0, 0 is some non-zero multiple of do I? Okay, no, this is fine. dy. Wait, I think I might have. Okay, yeah, that's fine. So, right, okay, no. This is what I did not, okay. What I wanted to write is if I take the derivative of LAB with respect to dxab, and then I plug in say b equal to 0, I get this, which is because a was not 0, this is some non-zero multiple of this derivative with respect to y. And now my assumptions on height pairing and using the work of Daniel, what I get is this plus the work of Daniel Dupigny will imply that this will have to therefore be non-zero. So that sort of is a quick sketch of how you get result 1. And once you have result 1 and result 2, you just finished on time. So yep, this is where I would like to end. Thank you for your attention.
Thank you very much. Other comments or questions?
Yes. Okay, so I know I'm on record and this is, okay, but I'll still say it. So when Mazur put forth these conjectures, people had not really studied supersingular ZP extensions, supersingular primes. So that was one reason why he had imposed the ordinary condition. So plus minus Selmer groups came much later due to Professor Kobayashi. So at the time of formulating the conjecture, people thought supersingular primes were a little difficult to study, so he did not include it. Yes, so then later, Antonio and Florian Sprung actually formulated it for the supersingular case, but they did not have any cases where they could prove it. They could say certain things about ZP2 extensions, but nothing about ZP extensions. And then last year, I had an opportunity to ask Professor Mazur this question, that if P was supersingular, should we at least even expect this to be true? And this is not written down, so I don't want people to quote me later that, oh, she said in this lecture. But what Professor Mazur told me that he would be very cautious to formulate this conjecture for supersingular primes. Yes, like there are clearly no counterexamples, but right. Okay. Yes. Yes, I like anything that I sort of prove assumed ordinary. Yes. I don't know if it's done. Yes. Yeah. Yeah.
Maybe a case is not self-dual case, so root number is not plus minus one, actually, just the root of unit.
Yeah, I think your mic might not be turned on. So Professor Prasad said he couldn't hear.
I think this GP extension is not self-dual, so root number is not plus minus one inch continuously. Yeah. KN, yeah.
Is it just saying that, I mean, it is non-degenerate? Yeah. The rank being 1 over, sorry? I haven't checked for an example, but there are algorithms to check these. As far as I know, there are algorithms. I think it is for essentially this sort of a setting due to Balakrishnan, Chipuriani, and Stein. They basically work in this sort of a setting. They do. Yes. Yeah.
Okay.
The cyclotomic case, you know that the height pairing is not algebraic on
Mhm.
non-torsional.
Mhm.
Do you know something like that in this study? That's the first question.
Is-
Second, when we wrote our paper, we had the most difficult part was to find numerical examples.
Yes.
Satisfied the hypothesis. How is the
Okay,
situation?
so for this one, we did not do numerical examples. For this paper, we did not do numerical examples. For the other one, numerical examples were not trivial to come by, but when we used the work of Nekovar, they were not impossible. But yes, coming up with examples was fairly difficult. Yes. Yes. Right, but I think what was important for us was to like have this more general setting where we could prove this result, because this is the one that we can actually now kind of generalize to a GL2, a abelian variety sort of a setting. That was sort of not possible with our algebraic machinery that at least we were using. Mm. If I remember correctly, Francesc has this hypothesis for sure. We were using his results. He was going to work with elliptic curves over Q. And maybe, yes, and maybe, but I think he works for elliptic, at least the way he writes down his paper, I think he works for elliptic curves over Q. That's possible.
Is there any questions? If not, then let's thank the speaker again.